Okay, so hi guys, my name is Shubham, and we did this project for restaurant informatics on Vision Transformer. We worked on a team of 3 people, me, Alberto Moccardi, and Yahya Momtaz. So what we did, we made the visual transformer, which is the new technique, state-of-the-art technique used for the classification on image. Before, CNN was the go-to method to work on the images. But after the very famous paper, an image is worth 16x16 word, the vision transformers were introduced. So since computer vision has changed since the introduction of this famous paper, and they introduced this novel technique where they employ transformers in images. In in images, what they do is they mm, break the images into patches and apply attention mechanism on that, and we got the very great results. As you can see on the ImageNet data challenge, there are mod swim transformer which is actually low in parameters and better performing as good as convolution models. What is there is swim transformer is just 80 million parameter model. It is because the attention focuses on pixels rather than the patches. So patches are 10 to more, rather like CNN focuses more attention on on pixels, but the transformer put the attention on the patches. That's why parameters are low. So as you can see, results are here. And then these are the roots. Transformers were introduced in Attention Is All You Need in 2017. And after that, it came to computer vision with a paper. An image is worth 16x16 word. So moving on, we use the PyTorch framework in where we get our data, we build the model, we evaluate the model, we see for the improvement, and then we use the transfer learning in the end to see the different results. And the methodology, we use the object-oriented programming, which works very well with PyTorch framework. And we can also subclass the already written modules of PyTorch. And of course, for this, we needed GPU. So we utilized the Colab pre-GPU to train our models because it was not that computationally good to train it on CPU. So we use the GPUs. And these are the table of contents, how we went through this project. First, we took the data, then we give the general overview of what we did, then the position embedding, attention mechanism, MLP, encoder, then we put through the VI, all this together, we make a VIT, then we do evaluation, then we do transfer learning, and then we compare the results. So I'll have my teammate, Yahya, to further explain from here.
Hello, I'm Yahya Momtaz, and I will continue our presentation. First of all, for data set, we use the Food 101 data set by Lucas Bozart that contains 101 categories of foods. But we use a sample data that has just 3 categories, pizza, steak, and sushis. Instead of 101 categories. And also we use the less than 300 images. Here we have tensors. Tensors convert our data to the numerical way. Here our vector is 3, which is color channel. Here our color channel is RGB, that it goes to 3. And height and width are 224. So our vector is 3, 224, 224. Okay. Because of hardware restriction, we use the data loader that allowed us to use 32 batches of data instead of 4 4096, and it's made our work easier. It made our work easier and just it. Okay, can you go to the next slide? For the architecture, the first is layers, that it has one input and one output, of course. Then we have blocks. A block has a series of layers. We give the input to it. It does some function, and then we have output. But generally, our model consists of a series of blocks that every input goes through our model. It does some function, and then we have output in the series of blocks. Here is the most important part. So first step is to divide the image into series of the patches. Then we need to flatten them and go through the dense layer. The result we get is a vector, and each vector relates to one image patch. Then we have class token that it has the class of object on any images. For example, sushi or pizza. Then we need to order the vectors. If you see the purple capsulate shape boxed here, we can understand that positional encoding are being done. Positional encoding is important because it holds the order of the vectors, and generally it improves our model accuracy. Then on the right side, we have transformer encoder. It has multiple layers. Each layer has one multi-head attention that followed by one MLP. Our model has 86 million parameters and 12 heads. Okay. Next, we have it's the go back. We have the MLP head. It's the final. It has a vector that the dimension of the vector is equal to the number of the classes, and it uses the softmax function. Okay, next slide, please. We use patch embedding. Patch embedding works is that, okay, it takes our image from 2 or 3 dimensions, and it's flattening it into 196 sequence in a flattening way. Then we have a vector with 196 and 786, which is embedding size. Okay, I told you before, positional encoding allowed us to improve the accuracy and holds the series of the vectors. But token embedding that we use, it's a learnable class. It allows, it's better than to just know one image. It's learned the representation of an image and update itself. Okay, for the next slide, Alberto will continue.
Yes, thank you, Yahya. I'm Alberto, and like all the other colleagues, I am a student of data science in University of Naples. Here we will talk about attention. But before to introduce the concept of attention, like it was exploited in the paper, we will talk about human visual attention. It's very trivial to understand from an image. Like in this case, we have pizza on a plate, in which pizza is the object of interest and the plate is our background. It's quite trivial to distinguish the object of interest from the background. We humans are all capable to understand this difference. But let's think about if we take 3 pixels from this image, like in the right side, we can understand that 2 pixels regarding the object of interest are as higher attention respect to the 2 pixels representing one the object of his interest and the other one the background. So this concept is enlarged through our VIT model. So basically, the VIT model analyzes all the patches of the image, not pixel because of this resource limitation, and search the similarities among the image. And finally, it finds out it average the original image built by each path of the pizza image in order to have an average score. But in which sense we can explain the similarity between two pixels or two patches? Basically, we can think about each pixel is a vector representation in a feature space. So we have on the left side the background and 2 pixels representing the pizza in this feature space. We can think about the similarities that are no more than a dot product between the pixels, so this vector, on the other vector on which we are calculating the similarity score. We can see that the pizza pixels has an higher projection despite the pixels representing pizza and the background. And this is no more than what we told before about the highest attention of the 2 pixels relating to the object and 1 to the object and background. In fact, we can see that this projection is lower regarding the pixels and the background despite the 2 pixels. Now, moving on to the next slide, we have the attention mechanism, how it is performed in our VIT model. And here we will explain each bricks of this attention mechanism. That is our principal layer of the VIT model. Here we have 3 main elements: query, keys, and values. These 3 elements came from the same root. This came from the input image that are flattened and they are represented as vectors. Now, these 3 elements basically are, there is a product between each of these vector for weighted matrices that are represented with the capital W, and it is different for query, keys, and values. This learnable representation of the input allows us to get an attention score. Now, let's figure out what are these main bricks of this model. The query is no more than the feature of interest coming from the input of our images. And then there is this multiplication dot product with all the other features of the other images represented by each patch. This product representing this similarity is then normalized by a normalization factor that was found out experimentally to be as the dimension of the key. Then this product that will represent the similarity between the query and the key is then performed a softmax attention function in order to squish to 0 those similarities that are lower and increase the value of this each pair of patch and key which present higher similarity. This product that represents the similarity between each patch and other patches inside our original image is averaged along the original feature that has to be scaled in order to have our attention score that are no more than a vector. So it's another representation of our input patch. So this is the mechanism. In this animation, we can see our input that is no more than a flattened vector. From this input will be taken the keys, values, and 1 query related to each of these input. The query will be multiplied by each of these key, and the output will be a score. Then this score will be then multiplied by each of these value, and the output of this multiplication that represent different vector for this different multiplication will be weighted sum, and the attention score will be the output of this attention mechanism. So this is, I will repeat again, this is no more than a different representation of the input patch in another representation that catch the similarities between the input query and all the other patch in the original image. Of course, these are learnable representation. This means that the matrices that perform this linear projection of the input are learned along the backpropagation process. Okay. Now let's explain what the multi-head attention mechanism is. This is the current state of the art of this BIT model because it allows, is an enhancement that allows the model to catch more patterns, more features inside our original data, proceeding in a parallel way. So the linear projection of the input will be done many times as we want. In this case, we used 12 multi-head attention. And this scaled product will be computed for each of these representation. Then the output will be concatenated and will be performed a linear projection in order to have the same output. It is no more than a different representation of our input patch. So let's move now to the second element of our transformer encoder. Since I explained the attention mechanism that represent the first step of our transformer encoder, we have to move now to the MLP. The MLP that will perform basically the operation with two connected layers with 3072 neurons, basically. The interesting aspect here is that in the paper were used GLU instead of ReLU. That's why, because of its nonlinear pattern that helps during the backpropagation process, and it is used a dropout layer with the rate 0.1 in order to avoid overfitting during the process. Okay, thank you. Now let's try to have a global view of the transformer encoder. Since we explained each bricks, now we will have this global representation with some improvements in the transformer encoder. Through the exploitation of the paper, we noticed that in the paper were used the residual connection and normalization layer in order to improve the performances of the model itself. The residual connection is very suitable for reduce the impact of vanishing gradient problem. In fact, it takes the input, it will perform the output through the MLP layer. Then the same input will be then skip these layers and going directly to this weighted product. Then instead the layer normalization, also used in this paper, will help generally during the training time and helps the model generalization. Now we explained the main ideas of transformer encoder. We have our BIT model that is no more than a model that has the input embedding layer, a stacked series of 12 blocks of transformer encoder, and an MLP head at the end that is able to perform prediction on our for our task for sure. And this model is, we can see here, has many trainable parameters. On the right side, in fact, we have the column of trainable parameters. And as also my colleague Yahya told before, there are 85 million. So it explains the weights of this model that is not very easy to train, let's say, in an organizational way, in an amateur way. I will give the floor to my colleague Shubham for the evaluation and of the training and the evaluation on the test set.
Thank you, Alberto. So as you can see, we were able to fully replicate the VIT base from the paper. Images were 16x6 and the total parameters were 85,800,000, which is exactly as mentioned in the paper. So now it's time to see the our model performance on our data and see how it works on our data. So as you can see, all the parameters are trainable. And let's see, we use the optimizer ADAM, which is the which is the most known optimizer, with a learning rate of 0.01, and the loss function negative log likelihood, which is categorical cross entropy because we have multi-classes. So as you can see, when we put our model for training, as you remember, our data is not that much because of computational problem. Our data has less images. So as we can see from the results, the accuracy, our model is severely underfitting, meaning that our model is not able to learn the image representations from the data. One of the reason might be that we have less data and the model is more complex, not able to generalize well. It will lead to bad generalization on the test data, which has not even seen yet. So moving on to the evaluation of this model, as you can see, our predicted images has same probability of same class, as it is predicting every image to be sushi rather than steak, which this needs to be sushi. This is correct. And pizza, which is sushi with same probability. So when we see this, what we thought of doing is why not implement the pre-trained same VIT based model from the torch vision models and see how it generalizes to our data and see if we can get better results. So moving on, we use the pre-trained weight, which we took from torch vision's model, and we applied sort of transfer learning. And what we did is we just imported the weight. We didn't tweak the parameters. We just use it as a feature extractor and put our data through it to learn the representation and think it will give us the better results. So the results what we got from using the pre-trained model were quite good. As you can see, we got around 90 to 93% of train accuracy and around 90 to 93 or 90 to 93 of test accuracy, which is better compared to the model which we used before. And then we tried testing the random images on the pre-trained model after saving, and see the results were quite phenomenal. As you can see this image, which has multiple objects actually, the people, the pizza cutting slices, it was able to predict it with around 99% probability of pizza. Same as with sushi, having just a little bit of a piece in the guy's forks, and still it is able to predict it with 84% probability. Same goes for steak with 98% probability, with most of the steak being in the image. And then we tried comparing it with the same state of the art IFNet P2 pre-trained model. There we also achieved the quite same accuracy. Only difference was VIT was little bit heavy in size, which is 327 MB, and the results were same. So comparing two of them, the VIT stands still ahead compared to CNNs because the parameters required in VITs are less, but the data and computation requirements are more. So if we are using generally, CNNs are better, but if you have the computation, you have computation power and GPUs, better to go with VITs. So that is the conclusion. And if you, that's pretty much it.